Thanks and good morning. Thank you for attending my presentation. It's really a big pleasure to be here on stage. The EVM is a groundbreaking piece of technology. It was designed with a minimalistic approach in mind and in a short amount of time to get the Ethereum off the ground. But it was not designed with the goal to support the heavy weight of smart contract technology 10 years later. For example, it is not particularly suitable for execution of zero-knowledge proofs or for the creation of zero-knowledge proofs. It is also not really suitable to efficiently execute cryptographic primitives or other compute-heavy smart contracts. And it's also not suitable for just-in-time compilation. In addition to this, Vitalik just recently put forward the narrative to replace the EVM with RISC-V. And he also famously did so very recently here in Berlin in a presentation. So what does all of that actually mean? And what about all the other virtual machines somewhere in between? That's what I'm going to talk about today. So welcome again to my presentation about virtual machines. I'm Torsten. I'm with Parity, where I lead the contracts team. And when it comes to the agenda for the presentation today, I will first give an introduction. I try to keep everything very lightweight, very approachable, also for non-technical audience, by the way. And then we're going to talk about VMs in general. I give an overview of the VMs that are used in the blockchain world. I will then talk about the very interesting topic of zero-knowledge VMs, and I will conclude with a discussion of interpretation versus compilation. First, I want to establish why we actually need virtual machines. Our goal is to execute smart contracts. And smart contracts are written in some source language, for example, Solidity. And the easiest approach would be to just take that source code and deploy it to a blockchain node or a validator node. That validator node has some CPUs, some native hardware, and that would then execute that smart contract directly. We could do that by having an interpreter that would then actually just interpret that source code directly. But that's not a good approach because it's super complex. The source language is quite complex in general, and another big problem is that we want to allow the source contract, the source language like Solidity to evolve over time, to get new features, to get more safe, and it would be super complex to keep track of all these different versions of the source language and allow to execute all of them. We don't want to have that complexity on the blockchain. Another approach would be to take the source language and to compile directly to the native machine code of the validator node. But again, that's not so cool to do because the blockchain network is heterogeneous. There are many different validator nodes that use different architecture, ARM or Intel or whatever. And that would mean that with this approach, we would need to compile the source code into all these different machine codes. And another problem is that we would need to ensure that they run always in the same way and that they have deterministic outcomes. Also very complicated. So the community settled on an intermediate representation, and that's the virtual machine. With this approach, we would compile the source code into a program of the virtual machine, which is called the bytecode. Bytecode is much simpler than the source language, and it's usually also fixed over time, so it doesn't have that many changes. And that makes it much easier to interpret on the blockchain or to execute on the blockchain node. Now that we know why we need virtual machines, let's look at what they actually consist of. If you want to define your own virtual machine, you would need to define the following components. First, you need to define the storage model. You need to define where values are stored and the different kinds of storages. We have, for example, a memory. We can have a stack or registers, and I will talk a little bit more about this later, what that actually means. Then we need to define the environment of the virtual machine. The virtual machine is usually encapsulated, and you see that there. The green boxes, by the way, should represent the memory, but the virtual machine is that rounded square, and the host environment outside of that would also sometimes need to interact with the virtual machine, and then you have this environment, and you have syscalls that you define that precisely specify how the interaction can take place. And then the most important part probably of a virtual machine is the instruction set. The instruction set is a complete set of instructions that's kept minimal. You want to keep it as simple as possible, but the instructions together are powerful enough to execute or represent every program they're Turing complete. And then you also need to define the semantics of these instructions. That means you need to define how an instruction gets executed and how it interacts with the memory, how it changes it. As a very simple example, I have a virtual machine with just two kinds of storages. We have a stack, which is a storage where you can stack values on top of each other and can take them away from the top. And then you have a memory with 4 cells that have addresses 0 to 3, and you can access them randomly. Then in this case, I have 3 simple instructions. I have a push instruction that allows me to push a fixed value on top of the stack. Then I have a pop instruction that allows me to take the uppermost value from the stack and store it in memory cell J. And I have an instruction called add that takes the topmost element from the stack, combines them by adding them, and puts the result back on the stack. And this very simple instruction set, we can have a program like this one, and I think it's quite clear what it does. First, we push the value 12 on the stack. Then the next step, we push the value 20 on the stack. Then we execute the addition operation where we combine these upper two values and have now only the result 32 on the stack. And with the final instruction, we take that uppermost value 32 and store it in memory cell 2. And the result would be the one that you see there in the storage. Of course, that's a very, very simple instruction set and not powerful enough to represent every computation. In a real instruction set, you have more operations. And also different virtual machines vary quite a lot in their instruction sets. But in general, these instruction sets do similar things. And you can roughly group them as follows. That's for the example of the EVM. First, we have the most obvious instructions, arithmetic and logic instructions for adding values, for example, or comparing them. Then we have some cryptographic instructions and primitives, for example, for hash values. Then we can have instructions that interact with the system to query a blockchain state, for example, what's the balance of that account, what's the current gas price. Then you have instructions to interact with the memory, store and load values. Then you have control flow instructions. That's quite important if you don't want to just have linear execution of instructions, but you want to break out of that and jump somewhere else or call into another contract. And then you have some specific instructions on some blockchains. For the EVM, you have log instructions, for example, that allows you to log values in a block. And finally, you have lifecycle instructions for example, for creating and destroying smart contracts. And one thing here is famously missing from this overview, namely these are floating point instructions that you would usually find in normal instruction sets for CPUs, but you don't want to have them for VMs that's used for blockchain execution because floating point instructions are usually not really deterministic and they might be slightly differently executed on different architectures. That's why we avoid them. We need determinism. And one thing that's also obvious for this virtual machine is that there are instructions that are blockchain specific. That's a feature of the EVM. It's not a feature of every virtual machine. Some virtual machines like WebAssembly are general purpose that are not tailor-made for blockchain execution. And for those virtual machines, you need to find some mechanism how you can have blockchain specific execution. Now let me also look at this environment that I talked about. I already said that VMs are encapsulated, or you say sandboxed. That means they can usually not interact with the host, and that's important because for security, you don't want that some untrusted source code or some untrusted code that anyone can upload to the blockchain can now just do random things on the host environment. And you also want that it runs deterministically on every node, and that's why you need this encapsulation. But sometimes you still need interaction with the host because you need to do some specific things that you cannot do if you just stay in this environment. And that would, for example, be for logging values to a block or to gas metering or also to hosting, to access the host storage, like some persistent storage between executions. I just mentioned gas metering. So let me also talk about gas metering. That's also something very specific for virtual machines that are used for blockchain execution. It's not something that you find in virtual machines per se. For example, in WebAssembly, you don't have gas metering built in. But you need gas metering for blockchain execution because we want to charge execution. We want that people pay if they want that the blockchain executes some smart contract. And you can call that as a pay-as-you-go CPU. Usually you want to charge for the time of the execution, but you also need to do this deterministically. And one idea is to use a gas value, you track a gas amount, and for every single instruction that's executed, you charge a small amount of gas. And that system has already been baked into the EVM. So in the EVM, you have this baked-in gas model, because the EVM is a virtual machine with blockchain execution in mind. And the idea there is just that every single instruction has a fixed amount of gas that you charge for it. I want to contrast this with virtual machines that don't have a gas model included, like WebAssembly. For WebAssembly, you need to do it differently. And one idea is to take your bytecode and then, before you actually execute it, to extend it, to add some extra instructions. And we already talked about host calls that we can do. And you would, in a WebAssembly environment for blockchain execution, you would have special host calls for charging gas. And we just add these host calls before every execution or before every instruction in our bytecode, and then we can just execute it. Here it's a little bit inefficient. We don't need to do it inefficiently. We can also combine instructions that are always executed in unison by blocking them. And we just charge gas once when we know that these instructions will always be executed together and there's no control flow instruction in between. This whole method is called instrumentation. And the good thing about this is that we just need to touch the bytecode and we don't need to touch the execution engine. The execution engine doesn't even know about gas metering. So this was the general introduction. Let's now look at the landscape of virtual machines used for blockchain execution. There are a lot of virtual machines, but I want to present the 5 most important ones, how I see it. First, we have the EVM, famously, don't need to go into too many details here, used for Ethereum, but also for all kind of Ethereum layer 2s. Then the next one would be the BPF, the Berkeley package filter. That's a virtual machine that was actually, is used for in the Linux kernel for filtering network packages, but it has been employed by Solana for blockchain execution. Well, BPF is really not made for blockchain execution and it needed to be tweaked in some sense, and the result is the Solana VM, SVM, and it's currently mainly just used in Solana. The next one is MoveVM. There's an interesting history to it. It has been invented in the Facebook project Libra. And something that's really cool about MoveVM is that it's really tailor-made for blockchain execution. It has security built in. It has concept of tokens, and a lot of things that could be insecure are already secure by design in MoveVM because it is really tailor-made for blockchains. And it's currently used in Sui and mainly in Sui and Aptos. Next one would be WebAssembly. Of course, WebAssembly is a famous virtual machine that's widely used outside the blockchain world. And for that reason, it's also widely supported with tooling. And of course, in all browsers and big companies support that. And for that reason, there was a movement in the blockchain world to use WebAssembly for blockchain execution a couple of years ago. A lot of systems migrated to WebAssembly, particularly also Polkadot, or at least Pallet Contracts and Substrate supports WebAssembly for smart contracts. Then you have Near, Stellar, and Cosmos with Cosm WASM, also ecosystems where WASM is used for blockchain execution. And then the final one, RISC-V, I already mentioned that with Vitalik's quote at the beginning to replace EVM with RISC-V. RISC-V is very promising and is currently used in Polkadot. That's not exactly right. It's actually in Kusama, the canary network of Polkadot. There you can already use it, and it's already also in Nervous CKB. RISC-V for Ethereum will take some more time, at least, I guess, 2 more years, but here you can already use it nowadays. I don't have time to look at all these virtual machines in detail, so I can only compare them on a high level. But I want to do some comparisons so that you see how they differ. And one way to compare them would be to look at some of the memory architecture. And the most important characteristics is whether they use stacks or registers for storing temporary values. If you do some calculation with multiple steps, you add values, you want to multiply them after that or whatsoever, you always have some temporary values in between that you need to store somewhere. And If you store them on a stack, we already saw that, how a stack looks like. You put items on top of that, you can take them away. And that's one way to do it. Another way to do it is to employ registers. Registers, when you have registers, you only have, the registers are memory cells, but they are very limited. You only have a few of them in such an architecture, like 10 or 20 or something like that. And every register also has a name, so you can name them directly and can say you want to store a value in that register or that one. Whereas for a stack, you cannot name the entries. You can always just refer to the top. And that's also why the bytecode usually looks quite different, whether you have a stack machine or register machine. For example, we already saw that example for a stack machine, but for a register machine, you would then say where values are stored and what register. We can just look at this example here. Here you push a 5 on top of the stack, then an 8, then you add them, you have the 13. For the register machine, the equivalent execution looks like this. You have this instruction li, load an immediate value 5 into register x1, then load the immediate value 8 into register 8, and then you have an instruction that says combine or add up the values in register x1 and x2 and store the result in register x3. So at the end, it does similar things, but you see that the way you address this memory is quite different. Another way to compare virtual machines is by looking at the word size. If you look at the memory inside of virtual machines, whether it's any kind of storage like memory or the registers or the stack, you will find that usually all of them have the same bit size. That's a fixed constant of the virtual machine. In EVM, that's famously 256 bits, which is massive, way more than you usually find somewhere else. And in RISC-V or other virtual machines, you just have 64 bits, sometimes 32 bits. Then one a little bit more technical term to compare virtual machines is to look at the endianness. The memory is a sequence of bytes, but sometimes you want to store something bigger that doesn't fit into a single byte. For example, a very big number like that one, that's hexadecimal, but doesn't matter. It's the number 1, 2, 3, 4, and so on. I want to store that in my memory, and I now need to split it up into bytes. I need to decide how, in what order I store those bytes. If I use the big endian order, I start with the biggest byte first, not by number, but by importance. And that's the one at the beginning. That seems to make a lot of sense. The other order is little endian, where I turn it around. It looks a little bit counterintuitive to do it that way, but it just turns out that most actual CPUs use little endian, and also most CPUs use 64 bits or something like this. So that's the reason why one would use little endian, although it looks counterintuitive. Now, if you go back to our VMs, then we can now compare them regarding to these characteristics. And I put different colors here. Green represents a color that you would usually find in a CPU. If you look at normal CPUs, like actual hardware, you will see that most of them use register architecture. They usually are 64 bits. And as I already said, they use little endian. Now, what you see is that EVM is going counter all these standards. It uses really big word size, big endian, and so on. And it becomes already apparent that if you want to execute EVM bytecode on a real CPU, you need to do a lot of extra work to execute it because the actual CPU is quite different. And that also means that EVM execution can be quite slow. And that's a good reason why you would employ other virtual machines. Now, one reason why you would use other virtual machines, I already said that, is for zero-knowledge proofs. So let me look a little bit closer at zero-knowledge virtual machines. Zero-knowledge is a fascinating topic, and I can really just scratch it at the surface and cannot go too much into detail. So the standard execution mode in blockchain is that you have a state machine, you have a state, then a transaction would transform that state into a subsequent state, and so on, and everyone would agree on the resulting state. In general, you can do this with a long chain of transactions. You start with a state, and everyone could then execute these transactions and would get to a resulting state. And that needs to be deterministic. But one approach to do less work is something that you find in zero-knowledge rollups. And here you compress all that work into something called a zero-knowledge proof. Cannot go into details how this is generated, but there's a lot of very complicated magic in the background, and that magic would generate a proof that's much smaller than these transactions. and everyone can now validate that the execution is correct, not by executing transaction by transaction, but by just looking at the proof, by looking at the previous state and by the subsequent state, and then you can check that this is really correct, that the execution was really correct and the subsequent state is really the correct one. That's exactly what happens in your zero-knowledge rollup. Now, the generation of that proof is very, very complicated. It takes a lot of computation time, particularly if you use a tailor-made, if you use just a normal virtual machine. So the message is that the EVM is not zero-knowledge friendly. It's super slow to generate such a proof. And in order to speed that up, you need to change the EVM slightly. Here's an overview. I don't want to go too many details, but there's an overview that Vitalik also put out. He grouped EVMs that are made or tailor-made for ZK, for zero-knowledge proof generation, into 4 different types. The first type is the one that's most equivalent with EVM, and the further you go down, the more you change the actual virtual machine to not be so similar anymore, but you have much faster proof generation. So in the 4th level, you have the fastest proof generation. An example would be Cairo Starnet. These are virtual machines that are similar to EVM, but you also have virtual machines that are similar to other, you have ZK virtual machines that are similar to other architectures. For example, a virtual machine tailor-made for zero-knowledge proof generation for RISC-V would be RISC-0. So my final topic is interpretation versus compilation. When you execute your smart contract, there are 2 ways to do it. One way is to interpret it. That means you go instruction by instruction. You have an interpreter that looks at every instruction, checks what the instruction is supposed to do, and executes that. It's a very slow process. The other alternative approach would be JIT compilation. That means just before you want to execute a smart contract, you compile it to the target architecture, and then you have machine code, and that runs much faster. This is really much faster. It's orders of magnitudes faster. But it turns out that almost all the virtual machines that are used in the blockchain world use interpretation, and the question is why? Well, the reason is that JIT compilation is really hard, and it usually takes a lot of time to do, and it's unpredictable how long it takes. And for that reason, you cannot do it in normal practical sense. There is one way to restrict that, and that's linear compilation. But linear compilation is usually not possible, particularly if your virtual machine is a stack-based virtual machine. The reason is that you need to transform a stack-based architecture into a register architecture, and this is an NP-complete problem if you're familiar with this, and that just means you cannot do it in linear time. So you can only do this if your stack-based, if your virtual machine that you look at is already a register-based virtual machine, and there are not so many of them. But one of them is RISC-V. And here I want to look at the example of the Polka virtual machine, PVM. This is a virtual machine used in Polkadot or Kusama, and it's based on RISC-V, and this one can be JIT compiled. And it's really hard to recognize here, but you see the uppermost bar, the blue bar, that's JIT compiled, that's the execution time of JIT compiled Polka VM, and compared to the execution time below of interpreted Polka VM. And that's actually a logarithmic scale, so that's much longer. And the compilation time is also quite slow, quite fast. That's the red bar. It's a really short bar to compile it. If you compare it to compilation of WASM code, it's much, much longer. So if you want to check it out, there's a preview of the Polka VM is already live on Kusama. There's a link here where you can see it. But I want to point out that it's not yet the JIT compiled model that's live, that will go live later. But at least you can play around with the Polka virtual machine. And with this, I want to conclude my presentation. Thanks a lot.